All right, we're going to take a look today at section 4.4, which is titled Complex Numbers. Before we talk about what complex numbers are, let's consider, we've been dealing with quadratic equations and solving them. So let's consider this quadratic equation. We'll solve x squared plus 1 is equal to 0. So we've solved this two ways. We've solved it by graphing and looking for x-intercepts, and we've solved it by factoring. I will tell you that if you try to graph this one, it's one of those where the parabola it opens. I don't know exactly whether it's left or, well, I guess I do know. I can fix that. Oops. It would look like this. So it doesn't have any x-intercepts. So we can't use graphing to help us solve that. So then we factored it. Well, what two numbers would I use here? What two numbers add to 1 or multiply to 1 and add to 0? Does it work to do -1, +1? If you take -1 times +1, you get -1, not the +1 that it gives us. This is not a difference of two squares, it's a sum of two squares. It's actually not factorable. So we couldn't solve this, and it's not factorable, partially because there's the same reason that we didn't have x-intercepts. So up to this point, we would have just said there's no solution, when in reality, what we really meant to say is there's no solution based off of the numbers that we've learned about thus far. And the type of numbers you've used in your entire math career, you haven't learned about a number that actually solves this, but you have somewhat of a limited knowledge base at this point. We're going to expand it today. So there actually is a solution to this. And so let me introduce it this way. Instead of trying to factor or graph, let's subtract 1 so we can isolate the perfect square. And then to solve that, we may want to consider using a square root. The square roots cancel out squares. But hopefully you remember this, that any time you introduce a square root to solve, we lose an answer. There's actually supposed to be two answers, so we have to put in plus minus. When you square root to solve an equation, we need plus minus. And so now we have x equals plus or minus the square root of -1. But what number can you multiply by itself and get -1 for an answer? Well, once again, that's where our current knowledge base fails us, and we don't know. We don't have a number that when we multiply it by itself gives you a -1. We can get a +1, but not a -1. And so I introduce the number I. The answer to that is I, positive or negative I. So I is defined as the imaginary unit. The imaginary unit I. Some of you may have heard people talking about imaginary numbers. That's what we get into here. I is an imaginary number. To be clear, I don't like that they gave it the term imaginary numbers, nor do I like the numbers you've dealt with up to this point being called the real numbers, because it seems to imply that those are real and this one's not. Whereas that's not actually the case. Maybe it's been the case in the math that you've dealt with up until this point, but there are real world applications to using imaginary numbers and complex numbers. If you go into engineering, some of you might be interested in going into engineering. Imaginary numbers might be a number you encounter. If you go into dealing with electricity, like electrical engineering, it definitely is a big part of what you'll encounter. So there are applications to being able to solve this type of problem. And a lot of people won't use them in math beyond this, but some people do. So that's why we talk about it. So imaginary unit I is defined as the square root of -1. Anytime we have the square root of -1, that's the imaginary unit, and we just use the letter I. So let's do a couple of simplifying problems where we make use of that. Let's consider the square root of -81. So I really want to separate the negative away from the 81. So when we see a problem like this, break it apart, break it into pieces. So we've got the square root of -1 times now the square root of 81. Square root of -1 times the square root of 81. We can break it into two parts. Square root of 81, hopefully you know, is 9. The square root of -1 we just introduced as I, and the square root of 81 is 9. The order that I write this, I like to write the 9 first and then the I last. So I would actually call this 9I. Notice I did not do a plus or minus here. We don't do pluses in the plus minus unless it's a problem with an x in it and we had to do a square root to solve it. Once again, back over here, I originally had x squared plus 1 equals 0. We were solving for x. This problem doesn't have an x in it at all. I'm just simplifying the square root of -1, 81. So the sign was originally positive, so the sign of our answer better be positive as well, because I'm not solving anything. Let's consider the square root of -32. So I can break it apart, square root of -1 times square root of 32, but this time 32 is not a perfect square. So can we break 32 down? You have to ask yourself, is there a factor of 32 that is a perfect square? 4 is, but there's actually a bigger one. I want to find the biggest one possible to make my job a little easier. It's 16. So 32 is 16 times 2. I can break it apart that way. Square root of -1 times square root of 30, or 16 times square root of 2. So now we get I times 4 times the square root of 2. And so the order, once again, I want the 4 in front of the I, but I like the square root last. So we would call this 4I square root of 2. Let's consider another simplifying problem where I take 4I and I multiply it by -3I. 4I times -3I. Think about what you would have if you had 4x times -3x. Hopefully you would say that's -12x squared. Similar. Here, 4 times -3 is -12. I times I is I squared. But I squared can simplify. In fact, anytime you have an exponent on I, it will simplify. Why is that? Let me scroll back. We'll come back to that problem in just a moment. But consider over here. if I had I squared, and we know that I is the square root of -1, that really means square root of -1 squared. And we know that square root and square are inverse operations. They undo each other, they cancel each other out, which will leave you with just -1. Anytime you have I squared, it equals -1. I'm going to add to those notes here in a little bit more further where I have I and I squared. We'll continue that. But let me come back to this problem because now we can finish this problem. -12 times I squared is actually -12 times -1, since I squared is -1. So we get our final answer, +12. This is a similar type of problem, but I have an additional step before I get to problem like number 3. It's really a combination of the first couple problems we did along with number 3. Unfortunately, you can't just multiply this all together and then simplify. You kind of have to treat it as 2 separate problems. So let's break apart the first part, the 3a squared of -24. So I'll have my -1. How can I break 24 apart? Is there a perfect square that's a factor of 24? 4 is, and then you'll be left with a 6. And then times, let's do the same thing with the 2. So we have 2, and then it was -18, so that's -1 times. How can we break 18 down? 9 times 2. Still think of it as just 2 separate problems. So then square root of -1 becomes an I, square root of 4 is 2, and then I'm left with square root of 6. So in total, the 2 times 3 can combine to make a 6, so 6i square roots of 6. And then I do the same thing on the right. Square root of -1 is I, square root of 9 is 3, and then square root of 2 doesn't simplify. So in total, that's 6i square roots of 2. So when we multiply them together, 6 times 6, 36, I times I squared, square root of 6 times square root of 2 is square root of 12. And then now I need to simplify that further. What does I squared equal? Equals -1. The square root of 12 can break down. Square root of 4 times square root of 3. So now 36 times -1 times 2 times the square root of 3. 36 times -1 times 2 is -72 square roots of 3. And there's our final answer. Next, let's look at I to the power of 40. And we'll look at I to the power of 63. I want to solve each of those. But let's think a moment. I'm going to scroll back. I said we'd come and add to the list we had over here. So I want to do that. Let's continue this list. So I is just simplified. I is I, but I squared becomes -1. I to the third. You can break I to the third down this way. You can think of it as I squared times I. I squared times I is I to the third. we know that I squared is -1 times I becomes just -I. I to the fourth, I can break that into I squared times I squared, which is -1 times -1, which is a +1. And then I start to see repetition happen. So I to the fifth can be broken down into I to the fourth. I like I to the fourth, so I break it down that way for sure. I to the fourth times I. I to the fourth we know is just 1, so it becomes 1 times I, which is just I. And if we go with I to the sixth, well, that's I to the fourth times I squared. I to the fourth is 1. I squared is -1. So we get -1. You start to see repetition. I to the seventh, what would that equal? Well, we can really just get rid of I to the fourth because we know that's 1. So we can think of I to the third, which is -I. I to the eighth, well, it's I to the fourth times I to the fourth, which is just 1. And it happens over and over again. We see this pattern. 1, I, -1, -I. And then it repeats. 1, I, -1, -I. I could actually go back. Just think of that as I to the first. What would I to the 0 be? If you don't remember, and this becomes a discussion more in a different unit, I'll explain why it's the case, but anytime you have an exponent of 0, it equals 1. So I can say this way, I to the 0, to summarize this, equals I, or sorry, not true, equals 1. I to the first power equals I. I to the second power is -I, -1, sorry. I to the third power is -I, and then the cycle repeats from there. If you think of those exponents as remainders after we divide by 4, that could be helpful. So let's come back over to the problems that I gave. Here's how we can take this. This is a big number. I don't want to go through all the way through. Instead, think about what happens if you take the exponent, the 40, and divide it by 4. What will the remainder be? 40 divided by 4 is 12. Does it have a remainder? We'd have a remainder of 0. So it's equal to I to the 0 power, which was 1. When you have 63, you take 63 divided by 4. 63 is not evenly divisible by 4. What is? 60 is. So what's the remainder? 3. So it's the same thing. It's equivalent to I to the third. What was I to the third? -I. We could do a couple more of these just for a little extra practice before we move on. This is actually a small part of the unit, but it is a part of the unit. I to the 14th. If you took 14 divided by 4, what's your remainder? Well, 12 is a multiple of 4, so 14 is 2 bigger than that. It's the same as I squared. What does that equal? -1. I to the 104th. Well, 104 is divided by 4. So it has a remainder of 0. So it's the same as just I to the 0, which is just 1. So we can make up any positive exponent and be able to figure it out because it's cyclical. Okay, now those are all imaginary numbers. And imaginary numbers and real numbers, when we combine them together, make up the group called complex numbers, and that's the title of the section. To introduce those or to talk about those, I want to think a little bit about a Venn diagram for a second. We have the group of real numbers that we've dealt with up in math all the way up until this point. We had some subgroups of real numbers, like we learned about, we've learned about integers. That's a smaller group. I don't want to write all these down, but we had rational numbers, we had irrational numbers, we had counting numbers, we had whole numbers. We have each of those type of numbers that are part of the real numbers. But now I just came and introduced to you imaginary numbers. So something like 3i, -7i, things along those lines. Now, what happens when I have a number that takes a real number and an imaginary number and puts them together? That's what a complex number is. That's what this unit is actually introducing. Complex number. So what does that look like? Something like 4 plus 2i. Notice the first part, 4, that's a real number. The next term, the 2i, that's an imaginary. It's a combination of real and imaginary. We could have 3 minus 6i, -2 plus 8i. Those are all examples of complex numbers. When one of the terms is missing, I either have just a simple real number or just a simple imaginary number, but when I have both parts, it's complex. The next portion of our notes, we're going to work on just different operations of complex numbers. Let me change colors. And in this section, instructions will still say to simplify. I'm not solving yet. I'll come back to solving. That'll be the last thing I talk about. That's when we kind of come full circle to what we were doing before this unit. For simplifying, I'll start over in my numbering. I could take something like -1 plus 5i. So that's a complex number, and add to it another complex number, say -2 minus 3i. When you add those together, this is probably the easiest part of this unit. It's as simple as combining like terms. So the real parts can combine together. -1 and -2 make -3. And then combine the imaginary parts. The 5i and the -3i make +2i. So there's our answer, -3 plus 2i. I could do a subtraction problem. 7 plus 4i minus 1 plus 2i. Subtract the real parts. 7 minus 1 is 6. 4i minus 2i is 2i. So adding, subtracting complex numbers, it should look familiar to us. It's the same thing as if they were x's instead of i's. It's when we get into multiplication and division that we have some new hurdles. Let's consider a multiplication problem. 6 minus 8i times 9 plus 2i. So to multiply these together, initially it looks, it's nothing new. It looks like the multiplication of binomials where we can distribute or FOIL or use a box method or lattice, whatever way you want to look at it. Ultimately, multiply your 6 times your 9, your 6 times your 2i, your negative 8i times your 9, and your negative 8i times your 2i. When you do that, we'll get a 54, a 12i, a negative 72i, and a negative 16i squared. Because negative 8i times 2i is negative 16i squared. Remember from above that we don't get to leave an exponent on an I. So we are able to simplify negative 16i squared. I squared is equivalent to negative 1, so that's really negative 16 times negative 1. So we have to think of that as plus 16. So now, combine like terms, 54 and 16 makes 70. And 12i minus 72i is negative 60i. And there's our answer. So you still FOIL or distribute, but then you have to deal with the I squared. Let's take a look at division, or sometimes written as in fraction form. 3 minus I over 4 plus 2i. Looks like a fraction, and we don't mind fractions for answers, but we do have pretty strict rules about what the denominator must be of a fraction if it's your answer, and the rule is your denominator needs to be a positive integer, and that's not the case here because I have a complex number. We're not allowed to have a complex number. So to rewrite this, we don't want to change the value of the fraction, but we want to change the way it's written. So we multiply the top and the bottom by some number. We have to figure out what to multiply it by. So I can't change the value, but I want it to be a number so that I don't have a complex number as a denominator in my denominator. And so this is a new discussion we haven't had yet. You may have had it a little bit in Algebra 1, and we'll have it later when we get into other fractions, x's in the denominators. But you may have learned about a conjugate. In this case, our conjugate is complex. It's a complex number, so we call it a complex conjugate. But if you don't remember what a conjugate is, it looks almost the same except for the sign in the middle. So I'm trying to do the conjugate of the denominator. So instead of 4 plus 2i, it's going to read 4 minus 2i. It's the sign between the real and the imaginary terms that switches. So that's called a complex conjugate. If we multiply it to the bottom, we have to multiply it to the numerator also. And we'll see why it works here in just a moment when I multiply. So now it becomes a FOIL problem again, or distributing problem, both in the top and the bottom. So it's 2 of them in one. So in the top, 12 minus 6i minus 4i plus 2i squared. We'll deal with that I squared shortly. In the bottom, 16 minus 8i plus 8i. Do you see right there why we use the conjugate? What's going to happen to those two terms? They're going to cancel. We have a negative 8i and a positive 8i. Those two are going to cancel out. We won't have an I term left anymore, and that was the goal. That wouldn't happen unless we use the conjugate. Then continue, 2i times negative 2i, that's negative 4i squared. Now we need to deal with our I squareds. We know that I squared simplifies. A positive 2I squared is the same thing as minus 2. And negative 4I squared is the same thing as plus 4. Those are both true because we know I squared is equal to negative 1. Now let's simplify both the numerator and denominator. In the numerator, a 12 and a negative 2 makes 10. Negative 6i, negative 4i makes negative 10i. In the denominator, 16 plus 4 is 20, and then our negative 8i and positive 8i cancel out as we already discussed. So now our denominator is a simple integer, which is what I wanted. Sometimes our fraction can simplify, and in this case it can. So I do need to do that last step. The only way it can simplify is if every one of the factors, every one of the terms rather, can be divided by the same factor. So in this case, I can divide a 10 to everything. 10 divided by 10 is 1, 10 divided by 10 is 1, 20 divided by 10 is 2. So that leaves me with 1 minus 1i. Well, I just write that as I. So 1 minus I over 2. And I am completely fine with that answer. I will usually write my answer in that form. But I also want to show you that our textbook would write the answer in a slightly different manner because they want what's called standard form. So let me show you what that would have looked like. So unless we have to give standard form, I would accept that. But here's what standard form would have been. Instead of writing it as one fraction, we would have broken apart the real part and the imaginary part. So the top was 10 minus 10i. Well, each of those will be over the denominator. So 10 over 20 minus 10 over 20, and then the I went on that term. And then simplify each one of those fractions. Well, 10 over 20 becomes 1/2 minus 1/2 I. That's the exact same thing that I have in the box above it, but the box above it is written as one big fraction. Down below, it separates the real part from the imaginary part, so it looks like a complex number. So we can do either one. I'll accept either one, but you should be able to recognize that they're the same thing. So those are the different operations we have with complex numbers. What we're going to do next is we're going to tie or kind of bring it full circle. Before this unit, we were solving quadratic equations, and we solved them by graphing, we solved them by factoring, but we had to interject this unit because sometimes our solutions are imaginary numbers. And because we talked about imaginary numbers, we went ahead and talked about complex numbers and included those as well. So they're a part of the unit, but the whole idea of this chapter is to talk about quadratics and solving them. So now that we've learned about complex numbers, let's come back and solve a couple of quadratic equations. I'm going to start renumbering again. Let's solve 4x squared plus 32 is equal to 0. This is another one of those. If I would graph it, my vertex would be above the x-axis. There are no x-intercepts. Same thing, it's not factorable. You could factor out the 4, but then you can't factor any further, so you can't actually get your answers. But if I solve this, I can subtract 32 from both sides. And right now, I don't have an x term in there, which enables me to do this. In a later unit, we will, but we'll approach that differently. But for now, I can just solve for the x. X squared by itself. X squared is equal to -8. Here's when I introduce the square root, because I'm trying to solve it, I have to get rid of the square. And when I introduce the square, that's when you have to do the plus or minus. So in the solving problems, we are getting rid of a square. That's when we have plus minus. Well, I'm going to break the negative apart from the 8. And the 8 can be broken into 4 times 2, because 8 was not a perfect square. So we get an I and a 2 and a square root of 2. So the order in which we want to write these, the coefficient or the integer first, that's the 2 first. Then the I comes before the square root. Square root goes last. So plus or minus 2i square roots of 2. So there were 2 answers. There was 2i squared of 2, and then there was negative 2i squared of 2. One more solve problem, and then we'll be done with notes. Sorry, we already did one as a warm-up. Okay, here we go. So let's go with 5y squared plus 20 is equal to 0. Subtract the 21st. And divide by your 5. Square root plus minus. Well, break the negative 1 apart from the 4. 4 is a perfect square this time, so I don't need to break the 4 down. We get I times 2, which of course we'll write as 2i. So plus minus 2i. So 2i and negative 2i are our answers. That's it for the notes for today.